All right, guys. So I want to review something. And what's interesting is that there's that one question on the test about the last so many years have had this temperature, right? It's that last question on that temperature problem. And I asked you if it's unusual. So there's multiple ways to answer that question. The question right before it, so for example, some of you guys had said the probability for the last 7 years has been 14.69 degrees Celsius, right? Or whatever, something like that, around that number. You with me? Is that unusual? And the problem right before it was the probability that a group of 7 years would have an average higher than 14.68, and you should have gotten approximately 0% chance, like 0.0001. So you could have used that result in the next question. Well, it's almost impossible for it to happen, so that if it does happen, that must be evidence something changed. You guys kind of with me? So if you're like, it's impossible for that to happen, and then it happens, doesn't that change your worldview a little bit? Well, then obviously it wasn't impossible. So I got to reevaluate what things are. So if the way temperatures have been says this is impossible or close to it, and then it happens, you're like, okay, all right, maybe it's by random chance, or maybe there's something to it. And that's something, whatever. I'll let you guys agree with the science or not. It's up to you. So, if I do this, what are you doing here? If I took, let's say I have a normal distribution. The mean is 70, and the standard deviation is 2.3, whatever. Okay. So here's a question we all should be able to answer. Between what two data points? Would we find 95% of the data? Whatever these data points are. So between what two data points would I find 95% of the data? So there's a problem just like that on the test. It was, I don't remember now. Well, it's sort of like find the temperature that would put a year in the top 6%, that kind of thing. I think it was on the quiz, I had one just like this. And actually, let me be a little more specific, the middle 95%. So what would that picture look like? The middle 95%. Yeah, I'm pretty basically drawing it for you, right? So it's normal, and then the middle 95% would be here. Is that cool? What are the z-scores associated with those endpoints?
25.
So let's back up a step. If there's 95% in there, how much is out there? 95% in the house, how much is outside the house?
2.5.
Okay, 2.5 on either side. I'm with you. So 5% out of the house, there must be 2.5 on that side. You guys with me? Does this feel familiar? We've done a couple of these kind of things. So this is 0.025. Can you look on your z-score chart? Figure out what that z-score is. It's going to be close to what we know. Empirical rule says, empirical rule says it should be 2, roughly. So whatever answer you get better come out close to 2, or negative 2.
That's on the negative side, right?
It's got to be on the negative side.
You said 2?
Yeah, I did. What is this? What is this? Physically, what is it? Is it a z-score? No, it's an area. So you look at areas in the body of the chart. You try to find 0.0250. What's the closest you can get to 0.0250? Did I bring a z-score chart for myself? Probably not. So I know what it is because it's one of the most familiar.
Negative 195.
Almost.
Negative 195.
Look. Can you guys all get that that's negative 1.96? If you didn't get that, look up negative 1.96. Doesn't it have about 2.5%? 0.025? There you go. What's this one got to be? Positive 1.96. Why? Because this is symmetric. Boogie woogie. Right? Okay. Do I stop there? Do I circle those? If these are grades, I hope to God negative 1.96 is a grade somebody got. It's like they misspelled their name or something. Left it all blank. So we got negative points. How do I change these into grades? Or whatever this is, right? I didn't say what it was. How do I change them into data points? So I gotta take a z-score back to an x. Yes. Alright, first little thing I want you guys to agree with me with. If we had a bunch of problems like this to do, it was the middle 95% and then the middle 90% and then the middle 98% and the middle whatever percent. The process would basically be the same. The only thing that would change is this number. Right? And what am I gotta do that equation how many times? Twice. I gotta go up 1.96 and down. So let me just do like this. Yeah, look at ooh. So I don't have to do that. I just do it twice, but just to get you ready for where we're going. If I'm going to do a bunch of problems like this, and every problem is the middle whatever, I'm going to go down and up the same number. In this case, that number is 1.96. So where's the negative positive? Well, it's frickin' there. So what number do I put in for z? 1.96. Not negative. It just has to be the number because the plus and minus is built in. You guys with me?
Yes.
A little bit. Some of you guys. Okay. So we haven't really done anything new yet. But I'm starting to change these a little bit so we're ready for the new stuff. All right, and then I can just plug this stuff in, right? So I get 70, give or take 1.96 of these 2.3s. And then whatever the hell that is. Now, real quick. It's been a while since this happened, but somebody actually did ask me where the plus minus button was on the calculator. So just to catch you in case you were about to ask, don't. You just do this twice. So my suggestion would be do this first, and then you can just add and subtract it from 7. So what is 1.96 times 2.3?
4.508.
4.518?
508.
08? Everybody else with us? If you need to borrow a calculator, might as well do it now. Because we're going to be doing stuff on the calculators. Doing stuff. Yeah. So then you would get, let me write it like this. I don't know if you guys remember this notation. So it would be 75.492 up to 74.508. Is that? Yeah, Jeff, 65. Good job, buddy. Is that right?
Yes.
I don't know if I trust myself anymore.
Did you do that in your head?
Yes. But I made a mistake, so don't give me any problems. What notation is that? Anybody remember? Interval notation. Kick ass. Interval notation. Because what's an interval mean? An interval of time has a beginning and an end. So that's an interval notation. That is an interval. So if these were grades, I would expect, how confident would you be that somebody's grade was in this interval?
Pretty confident.
Exactly how confident would you be?
95.
95% confident. You guys see that? Because what's the chances that somebody's grade is not in there? 5%. Because we just caught the middle 95% of all grades. On whatever this thing was. Okay. You guys, everybody with me? So we actually just did nothing new. I am saying things in a weird way, but it's getting us ready for what's coming. So here's the first little, or actually the second little tweak here. Because the first tweak was this dude. Second tweak is, this is part A. Here's part B. We take a sample. Today's, yeah. I was going to say today's not a good writing day, but any day's not a good writing day. We take a sample of 17 of these data points. Between what two data points would we find, too many words, 95% of the average of the sample means? So this was between what two data points where you find 95% of the individual scores, right? So that's why I said if it took one person, how confident would you be their test grade was in here? 95% confident. Let me stop right there for a second. Everybody cool with what's happened so far? Before we even get into that second question. If I catch 95% of the data, how certain am I that I caught a certain person's data point? 95% sure. Okay, I like it. What's going to change on part B?
It's a sample.
It's a sample. And I'm asking about the
Sample.
mean. Therefore, what has to change?
Standard deviation.
Standard deviation. And what's it become?
Standard deviation divided by n.
And I try to warn you guys, if you ended up dividing by the square root of something that wasn't a whole number, that was an immediate red flag. Because n has to be a whole number. It's counting things, right? Some of you guys divided by whatever you happen to see first, I think. Well, it's whatever n was. So on your test, n should have been 6, 7, 8, 5, whatever the number of years was. That was the sample size. So you should have taken this standard deviation divided by square root of 5, 6, 7, 8, whatever version you have. Okay. So what do you get in here? So it'll be 2.3 divided by what?
17.
Square root of 17. Kick ass, because that's n. And whatever that is. That was anti-chemical. Just need a little help. That'll be 0.57 something. 5. So 8. All right.
You never know what place to go.
Yes, you do. Standard deviation. How many places? At least.
3.
And then what is it we just calculated? It is a standard deviation. All right, so stop. We're about to get into territory where we'll see what happens. So then I do the same thing, don't I? Except what's going to change? What's the little tweak that I got to make to the formula? It's going to be mu plus or minus z times the new standard deviation, right? What's up? What do you mean? Well, we already did that part, so we're just going to put the number in there. Not a big deal. But I do want to get you ready for the formula we're going to use. And it's going to look exactly like that, almost exactly like that.
Is
So
that a new one?
Second.
We haven't used that one before, right?
That's an option. Some of you guys did that on the temperature problem. You could have figured out what was unusual.
Oh.
But you had to multiply by the new standard deviation because we were talking about groups of size, in your case, 5, 6, 7, 8. So some of you guys added 2 of the old standard deviations. We're talking about a group. You can't use the old standard deviation. Okay. And then whatever the shit, I almost don't care what the answer is here because it's the most important part is the idea. But what do you get as an answer? Just a 7, 8, give or take. What's Z going to be? It's still going to be in the 1.96. Why? I still want to catch 95% of the data. And to do that, how many steps do I take? 1.96. What's changing is how big each step is. And again, if I take 17 grades, is it more likely or less likely that their average will be far away from the real average? So could one person have gotten a really low grade? Yes. Could 17 people likely have gotten a very low average grade between all 17? No. They're more than likely going to be closer to the mean. Therefore, this interval should be smaller. Because it should be harder for a group to get really far away from the mean. So where would I expect 95% of all groups of 17 should be a smaller interval? So let's see. 1.96 times 0.558. And then, whatever that is. Again, this sounds funny. I don't care, really, because we did the most important part, but now it's just numbers who cares. Anybody doing that for me?
68.906 and 71.094.
I like it. That's fine. Couple places. Yeah. Okay, now, so let's get into what we're talking about today. So look at where we ended up here. We ended up with this. Right? So, I'm going to try to explain this the way I did yesterday. Let's see what happens. Let's say that we are, should I use the shirt one? Are interested in, well, actually, let me do it like this. I don't have to be too specific. What this is going to do is if I have a mean and my distribution is normal, if they don't say the distribution is normal like I did on the problem we did, what's got to be true to save our ass?
Sample size.
Sample size got to be bigger than 30. Keep ass. All right. So they don't say it's normal, the sample size better be bigger than 30. If they say it's normal, why was nobody concerned that this was only 17? Because again, they said it was already normal. I didn't need to make it normal, it was already normal. So what this will accomplish when I do it is it'll go up and down enough to catch a certain percentage. If I want to catch, so 95% was up and down 1.96. I really want you guys, so if I go down from the mean and up from the mean 1.96 standard deviations, I catch 95% of the data. Which is why we call 2 unusual, right? If I catch 95% within 1.96, anything outside of 2 standard deviations is going to be kind of unusual. Yes, no, maybe so? Okay. So if I wanted to be 98% confident, would I go further out or not as far out? So here's something. Let me say this. I hate fish. Not like I want to go kill them, but I don't like the taste of fish, right? And then everybody I talk to is always like, well, you haven't had the right fish. You need something less fishy. Well, that doesn't make any sense. Anyway, so if you like fish, great. I don't. So I save money. That and smoking, my God. If I did those 2 things, I'd be out in the street. Sorry. But I like this example for this. Even though I hate fish, I often think of these intervals as throwing a fishing net out. So if there was a certain fish that you really want to catch, that type of fish, and you want to increase the chances you do, are you going to go throw out a bigger net or a smaller net? Bigger net. So the more confident you want to be that you caught something, your net's going to get bigger. So of course, if this is 95% and I want to catch 98%, I'm going to have to go further out, which means my z-score is going to become bigger. It's going to be further away from the middle. The more shit I catch, the more sure I am I caught a particular particular thing, right? Okay. All right. So, normally we don't know what this is. So really what we're doing right now is we're transitioning from knowing everything into more realistic situations. When I go explore a situation, I want to go see the average parts per million of lead in some water to make sure that it's not going to hurt somebody, right? You can have a certain amount, just like you have a certain amount of rat feces in your food, and then it's fine. Think about that next time you're at a restaurant. I still eat there, so it's all protein. That's gross, Jeff. I don't know. Oh well. So, let me think. I forgot what I was talking about. That's fantastic. I got too hung up on rat feces. That's fantastic. What was I saying? I need to play back. Huh?
You're talking about the confidence of how much you're going to catch.
Okay, I'm sorry. So let me start over. Sorry, guys. So the whole thing about, we got about the bigger the confidence you want to be, the further out you go, so you catch more stuff. I'm not sure where I was going after that. This is what it was. We normally do not know what that is. We normally don't know what the population mean is. Just like the average amount of lead in water. So what do? We go out and do the next best thing. If I don't know what the real mean is, I'm going to take a sample and find, of course, sample mean. That's my best guess for what the real mean is. If I sample randomly and really work hard at making sure it's a random sample, then my mean should be close to the real mean. Would you put money on it being exactly equal to the real mean? No, good, because you're smart people. You're in my class. We talked about this before. It should be close, but I'm going to put a ton of money on it not being equal to. Because any sample I take, random fluctuations is going to be a little bigger, a little smaller. It's just the way it is. All right, let me stop for a minute. You guys with me? So a lot of what I just said is stuff we've talked since day one. So what's new is, I normally don't know this. So I go in not knowing where the middle is, and I get an X bar. So I go take a sample, N big, and I get a sample mean. So what we do, instead of using mu, we use X bar. That's my next best guess. So what I'm trying to do with this thing then, is I'm trying to create an interval that I'm a certain level confident that that interval has the real mean in it. So let me come at this a different way. So I have average level of lead in water. There's a real mean somewhere. I don't know what it is. I go take a sample and I get this. And then I construct an interval around it. And if I make a 95% interval, right, using the 1.96, I'll be 95% confident that my interval caught the real mean. Let me say that again. So if I make a 95%, and I'm gonna call it what it is, confidence interval. If I make a 95% confidence interval, then I'm 95% confident that my interval catches the real mean. Because again, why does that make sense? My X bar should be close to the real mean. So it should be really unlikely that my X bar is so far away that when I make an interval, it doesn't catch the real mean. Couldn't somebody else though, so let's call this X bar 1, this is us. and somebody else takes a sample and they get there, and when they make an interval, does it catch the real mean? No. And if it's a 95% confidence interval, what percentage of them should fail to catch the real mean? 5% should fail. There you go. So if I had 100 people create their own confidence intervals, take their own samples of the water, about 5% of them I would expect to not contain the real mean. So what we're doing, I really want you guys to realize, there's a number I don't know, there's a mean. The only way to get it is to get the entire population. Do we have time to check all the water in existence? Some of you guys are just nodding. Yeah, sure, we can do that. Let's do it. Let's go. Instead of being here, anything, just please. Door open now. No, stop. There's no time, right? We can't do that. So we have to do the next best thing. We have to take a sample, but our sample could be off, but it shouldn't be so far off that my interval doesn't contain it up to a certain level. So if I made a 90% confidence interval, what percentage of those intervals that people make would not contain the real mean? 10% of them. I like it. Okay. So let's try a real problem in this budget. Because I've been talking about ideas. This is the official formula. Look at this. Spare no expense. This is the official formula for confidence intervals for me. We will end up with 3 of these bad boys. 2 of them for means, and 1 of them for percentages. I think I've asked this question before. Anybody paying any attention at all to the upcoming election? So anybody? Some of you guys are like, I am actively not. Giant meteor, 2020. Start over. All right, it's fine. Are some of you guys actively looking or finding it hard to not hear about it? Anybody? You guys heard about any polls? Anybody ever hear about it? Look them up. Yes. So you see, like 44% would vote for Biden, and feel how you want to. 48% would vote for Sanders. Perfect. Sorry. So there will be a formula that has a percentage in it, blah, plus or minus, blah, blah, blah. And that will explain where that plus or minus 4 comes at. If you ever looked at a poll, they say 38% want this, and 40% want this, and at the bottom it says plus or minus 4 points, 4 percentage points. Right? Where the shit did that come from? We're going to actually see the formula that leads to the number. They didn't just make it up. As I pass out. Okay, so let's try a problem out as I do what I can for this thing. So here's a formula we're working with. Here's what a problem will look like. So we take a sample of 62 students and find an average test grade of 71.7. We know that the standard deviation of all grades is 12.29. So just to let you know, so the fundamental part of this whole problem was we don't know what mu is. We normally don't know what the population mean is. I'm hoping somebody out there is like, what about that shit? We normally don't know that either. But sometimes we do know this. Right, so there could be, like, do we know the standard deviation of men's heights? Yes. You guys with me? We know the standard deviation of men's heights. I could go to a specific town, take a sample of those people, and get an X bar, but why would I use RS when I know what sigma is for all men? So there are situations where we don't know mu, but we do happen to know sigma. Okay. The next formula for this we're going to use is going to be what happens if I don't know sigma. What if I only know S? I'm going to have to cover my ass somehow for that. All right. We don't have to worry about that yet. Not today. Blah, blah, blah. All right, I gave you enough information. So now construct the 90% confidence interval. I'm going to use the word letter CI for confidence interval because the less writing I do, the better for everybody. Bless you. So let's summarize what it is I tell you. Yeah, what's CI mean?
Confidence.
Confidence interval. Okay, I like it. Not CSI. So let's summarize what I've told you. What's X bar? 71 plus 7. What's N?
62.
62. What's sigma?
12.20.
12.29. I love it. This step is a very good step. Summarize what you were told using the appropriate symbols. That's the step people skip and they make mistakes. Why am I allowed to do this problem? Besides, well, you're doing it, man. We must be allowed to. I haven't done anything yet. Why am I allowed to continue? Yeah, n is greater than 30. If n was smaller than 30, do I say it's normal anywhere? Nope, so we couldn't do shit. At least not in stats 1. In stats 2, we don't teach, so too bad. Maybe someday, I'll see. Stats 2, you learn some tweaks to all kinds of shit. Just, what do you do when this is weird? Oh, okay. All right. Do you see how I got everything I need for this almost? Do I have this? Check. Do I have this? Check. Do I have this? Check. You can point to the right thing, Jeff. There it is. I don't have this. How do I get this? Yes. The confidence level tells you how far you want to go out. How big of a net do I want to throw? A little smaller than before. I don't want to be 95. For some reason, I just want to be 90% confident. So I want to see what the z-score is. How far away from the mean do I get for that net to catch 90%? It's going to be a little smaller than 1.96 because that caught 95%. I want to catch a little less. So can you guys figure out? And again, if you want to, if you draw the picture, what's it going to look like? Again, I know it's this because n's greater than 30. I want to catch the middle 90%. Does everybody understand why I can't just look up 0.9 in the z-score chart? What kind of area does the chart understand? It only understands the